One question we've already asked is, what happens to the term of the sequence, to the terms of a sequence, as they go on? We're going to talk about some limit laws, and almost none of them are going to be surprising. Mostly they tell you you can do the things that you intuitively want to do. Let's start with this sequence. This is explicitly defined, so it's pretty straightforward to write out the first couple of terms. If I start at 1, this is 1 over 3 to the 1 plus 1, which is a quarter. My second term is 1 over 9 plus 1, which is a tenth. My third term is 1 over 27 plus 1, which is a 28th, and so on. And we can graph these. Quarter, tenth, a 28th, and so on. We said that one way of thinking about sequences was as a function whose domain is only the whole numbers, but I can just as easily turn this into a function whose domain is much bigger. I can compare this to 1 over 3 to the power x plus 1, and I could put really any x that I wanted in there. And I can see that these behave quite similarly. As x goes to infinity, this function goes to 0. The denominator is getting bigger and bigger, so the whole fraction is going to 0. And exactly the same thing happens to the terms of my sequence. They get closer and closer to 0. So no surprises there. Now let's think about this sequence. This is again explicitly defined, so you should be able to figure out very quickly these three terms. Take a second, pause the video, find the first three terms. B sub 0 is sine of 0, which is 0. B sub 1 is sine of pi, which is 0. B sub 2 is sine of 2 pi, which is still 0. So actually this sequence is just the list of numbers 0, 0, 0, 0, 0, 0. If I wanted to sketch it, B1, B2, B3, B4, B5. But what if I compare this to the function that has all real numbers as its domain? If I'm no longer restricting my domain to only whole numbers, then my function gets much more interesting. In particular, when I consider the limit as x goes to infinity of the function that includes all these in-between numbers, this limit does not exist. I cannot evaluate that limit. On the other hand, if I take the limit as n goes to infinity of my sequence, well, it's 0, 0, 0, 0, 0, 0, 0. That limit is just 0. So the one time we have to be fairly careful is when my function, defined everywhere, does not have a limit. Then it is sometimes possible that my sequence does have a limit. Sometimes it doesn't. Oops, sequence. Oh my. If I take the function, the one that's defined everywhere, and that has a limit, then my sequence has that same limit. And it works the way you'd like it to. The only time you have to be careful is if your function, defined everywhere, doesn't have a limit. Let's compare these very similar looking sequences. Here's sine of pi x. So if I take b sub n, its terms are 1, 2, 3, 0, 0, 0, 0. This is the one we saw before. Here's just sine of x. C sub 1 is this number. C sub 2 is this number. C sub 3 is this number. C sub 4 is this number, and so on. We don't have this nice behavior that we had with b sub n. These jump around. They're not getting closer to any particular value. So although the limit as n goes to infinity of b sub n is equal to 0, the limit as n goes to infinity c sub n does not exist. These numbers aren't converging. They're not getting really close to one particular number. Rather, they're moving around without getting closer and closer to 1 point. For evaluating sequences like this, it's really helpful to be comfortable sketching functions. Then you can just look at them and it becomes fairly clear what happens to the sequence over time. Here's a theorem from your book that basically says the following. As long as the limits of these pieces of sequences exist, we can combine them in exactly the way you want to combine them. I'll show you an example. Here are two sequences, e to the minus n and 1 plus n over n, and their limits exist. So if I take these sequences and I take the 1000th term of this sequence, it's going to be pretty close to 0. The 1000th term of this sequence is going to be pretty close to 1. We can make a sequence by combining them. So this is a sequence. I plug in n equals 1, I get some number. Plug in n equals 2, I get some number. And I can combine them in exactly the way that I would like. This goes to 1 and this goes to 0, so this limit is 1 minus 0. That's what this limit law is saying. Now I want you to think about this limit. First, think about how do you combine these two sequences to get this sequence, and then how do you combine their limits? I can write this as e to the minus n times 1 plus n over n. I know that e to the minus n goes to 0, 1 plus n over n goes to 1, so this limit is 0. And that's what this law is saying. If I multiply two sequences, the limit of that product is the product of the limits. Using what you've just learned, take a second, pause the video, and evaluate these limits. This is a very well-behaved function. Whether I'm thinking of a sequence where I'm only plugging in whole numbers or whether I'm thinking of a function, it doesn't matter. What's going on the bottom is getting really big, so the fraction is getting really small. As n gets really big, this looks more and more like 0. On the other hand, for the second one, as n gets really big, this just gets bigger and bigger, so this limit is infinity. For the third one, we have to look a little bit into the fine print of those limit laws. I need these limits to be real numbers, and infinity is not a real number. So in this third case, I can't just say infinity times 0 is 0 or infinity times 0 is infinity. I have to be a little bit more clever than that. Infinity times 0 is not defined because in different instances, it's going to give you a different number. In this instance, I can rewrite this limit. While the n squareds cancel, this is just the number 2. So this sequence, when n is equal to 1, the term is 2. When n is equal to 2, the term is 2. When n is equal to 3, the term is 2. And when n is equal to 4, the term is 2. This sequence is just 2, 2, 2, 2, 2, 2, 2, 2, 2, so its limit is 2. Again, you have to be careful with infinity times 0. Sometimes it's 0. Sometimes it's infinity. Sometimes it's 2.